Welcome back to Discrete Structures. In this video, we'll be discussing slide set number 19, which is posted on Canvas. Also, remember to check on Canvas the deadline for assignment 6, which is ongoing, as well as the daily Zybook assignments that you must complete on time. So in this lecture, we will be discussing 3 properties of functions. At this point, I assume that you have watched video number 1. I put a link to that video in the description of this video, and it contains detailed definitions of these properties, which I'm only going to summarize here. So first, we say that a function is onto if its range is equal to its codomain. So one other way to say that in logic is to say that for every element C of the codomain of the function f, there exists an element D of its domain such that f of D is equal to C. Visually speaking, when looking at the arrow diagram representation of the function f, it just means that for every element in the codomain of the function, which we usually draw on the right, there is an arrow pointing to it, or at least one arrow pointing to every element in the codomain of the function. So another name for this property is surjective. So a function is surjective or onto if it has this property that its range is equal to its codomain. The second property you need to study in video number 1 is when a function is one-to-one, which means that it maps distinct elements of its domain to distinct elements of its codomain. So one way to state that in logic is to say that for every elements D1 and D2 of the domain of f, if D1 is different from D2, then it must be the case that f of D1 is different from f of D2. To visualize this, in the arrow diagram representation of a function is one-to-one where every element of the codomain has at most one arrow pointing to it. So another name or synonym for one-to-one is injective. Finally, we say that a function is a one-to-one correspondence if it is both onto and one-to-one. Remember that if a function is onto, it means every element of its codomain has at least one arrow coming into it. And if a function is one-to-one, then every element of its codomain has at most one arrow coming into it. So a one-to-one correspondence is a function for which it is true that every element of its codomain has exactly, that is at most and at least, one arrow coming into it. Now the reason this is called a one-to-one correspondence is because since by definition a function has exactly one arrow leaving each and every element of its domain, when it is both onto and one-to-one, that means there is a single arrow connecting each element of the domain to exactly one corresponding element in the codomain. So that's the reason for the long name one-to-one correspondence. And another name for these functions is to say that they are bijectives or they are bijections. Now, assuming that you are comfortable with these definitions, we're going to complete a bunch of practice problems by which you will develop the skills needed to not only determine whether a function has or does not have one of these properties, you will also be able to prove it one way or the other. So this will be a chance for us to, again, practice writing proofs, but in this case, pertaining to properties of functions. So for example, consider the function f, whose domain and codomain are identical, namely the set of binary strings of length 3. The mapping that f represents is described as taking a string in the domain and moving the second bit of that string to the last position in the string. Another way to say that is f will take a string of length 3 and it will swap the last 2 bits of that string. So now I want you to pause the video and determine which properties this function f has, and then to pick the correct answer here. So hopefully you did your homework and you found out that this function is both one-to-one and onto. In other words, it is a one-to-one correspondence or bijection. So what that means again is that for every element of the domain, there is exactly one corresponding string in the codomain and vice versa. So I'm not going to prove this here. This will be a homework problem for you. But what I want you to do is to go back to the definition of one-to-one as it was written in logic and use that definition to write a complete proof meeting all of the requirements that we have laid out in this course so far. And then secondly, I want you to do a proof also of the fact that this function is onto. Let me mention that in videos number 2 and 3, which I have linked to in the description of this video, you will find example of proofs pertaining to similar properties of functions. So I expect you from now on to have watched these 2 videos before moving forward. For this question, let's consider the function f, whose domain and codomain are both the set of binary strings of length 4. And the mapping that f represents is simply the action of taking a binary string and replacing the last bit in it with a 1. So of course, if the string already ends with a 1, then it is mapped to itself. And that is a pretty simple definition of f. So again, I encourage you to study this function, determine whether it's one-to-one and or onto, and to choose the correct answer here. So hopefully in this case you found out that the function is neither one-to-one nor onto, and I expect you to pause the video and to write complete proofs of these facts before moving forward. So as an example here, let me prove one of these statements, namely that f is not one-to-one. So in this case, we can use a proof by counterexample. Since the definition of one-to-one says that f must map distinct elements of the domain to distinct elements of the codomain, we can simply find and exhibit a counterexample. So if we pick the element of the domain, say 0, 0, 0, and then the second element 0, 0, 0, 1, let's call this string D1 and this string D2. Notice these strings are identical except for the last bit. And then when we apply f to D1, we get the string 0, 0, 1. And when we apply f to d2, we also get 0, 0, 1. So what we notice is that d1 is different from d2, but f of d1 is equal to f of d2, and that's enough to show that the function is not one-to-one. So again, I encourage you to go back to the formal definition of one-to-one, and you'll see a conditional. And then this is the antecedent of the conditional, and this is the negation of the consequent of the conditional. Therefore, this is a counterexample to that definition.